Welcome to RMK CET. I am Pratima, Assistant Professor in ECE Department. I am dealing the subject Signals and Systems. In this video lecture, we are going to see properties of Fourier transform. This is the topic under our second unit. The following are the properties of Fourier transform. First one, linearity property, time scaling, time shift, time reversal, convolution, multiplication, differentiation, integration, time multiplication, Parseval's theorem and duality. Before going to see properties of Fourier transform, we will see first of all the mathematical equation for Fourier transform as well as inverse Fourier transform, that is Fourier transform pair. X of j omega equal to integral minus infinity to infinity x of t e power minus j omega t dt is the Fourier transform equation, and small x of t is equal to 1 by 2 pi integral minus infinity to infinity x of j omega e power j omega t d omega is the inverse Fourier transform equation. X of t, if we apply Fourier transform, we will get capital X of j omega. If we apply inverse Fourier transform to the x of j omega, you will get x of t, and this is the Fourier transform pair. First one is Fourier transform analysis equation, and second equation representing synthesis equation. Fourier transform analysis and synthesis equations. So this is about Fourier transform pair. Now we will see first property, linearity property. So linearity property means anywhere if the system satisfies homogeneous and additivity property, then it is said to be linearity. Similarly here also Fourier transform, if it satisfies additivity as well as homogeneity, that means a Fourier transform of two functions, sum of two functions is the sum of Fourier transform of the individual functions. And also if you multiply function with a constant like alpha, beta, you will get Fourier transform is also multiplied with alpha and beta. That is Fourier transform of alpha plus alpha x1 of t plus beta x2 of t is equal to is nothing but alpha into x1 of omega, beta into x2 of omega. X1 of t Fourier transform is x1 of omega. X2 of t Fourier transform of capital X2 of omega. So if you apply the sum of two signals x1 and x2, you will get Fourier transform also added. If you multiply any arbitrary constants, you will Fourier transform also will get multiplied by same constants. This is nothing but linearity property, since Fourier transform is a integral equation. Next property, time scaling property. Time scaling property is nothing but x of t by a. Fourier transform is nothing but a into x of a omega. For example, to prove this property, let y of t is equal to x by ta. Apply Fourier transform for this signal. So x of t by a, this is the Fourier transform equation. Integral minus infinity to infinity x of t by a e power minus j omega t dt. Let t by a is equal to a variable u, then t will become au and dt will become a into du. So t by a, we have assumed it as u. So substitute t by a is equal to u. So t will become now au and dt will become a into du. So that is equal to a will come outside, integral minus infinity to infinity, a is constant, x of u e power minus j omega a. If you write this like this, e power minus j omega u du, so it looks like in omega place a omega is there. So you can write it is Fourier transform of x of omega a. In place of omega you will take omega a. So Fourier transform of time scaling version is equal to, here also frequency scaling. Here it is t by a means here omega into a. Here at means here omega by a. Vice versa you will get. This is time scaling property. Next property, time shift property. What is this expression? X of t minus a. T minus a means time delayed version. So for this, if you apply Fourier transform, you will get e power minus j omega a x of omega. This is the proof for that time shift property. Y of t is equal to, let y of t is equal to x of t minus a. So apply Fourier transform. This is the Fourier transform equation. Y of omega is equal to minus infinity to infinity, whatever the signal, x of t minus a into e power minus j omega t dt. So here let t minus a equal to a variable u, so that t become u plus a and dt will become du. So dt will become du here. Here a will not be there. So integral minus infinity to infinity x of u e power minus j omega u plus a, in place of t a du is equal to e power minus j omega a minus infinity to infinity x of u e power minus j omega u du. Here a is constant, so with respect to u, omega is also a constant. So we can write outside of the equation e power minus j omega as outside the integration. So e power minus j omega into, this is nothing but Fourier transform equation. Integral minus infinity to infinity x of u e power minus j omega u du. In place of t there is u. So it is nothing but Fourier transform equation. So time shift version, if you apply, you will get e power minus j omega e x of omega. It is very important property. Throughout our third unit we will use this property. So it is nothing but, in text it is nothing but, in words it is nothing but, if a function is delayed in time, this corresponds to multiplication by a complex exponential in frequency domain. If t plus a is there means you will get e power plus j omega a. T minus a is there means you will get e power minus j omega a. So t minus 2 is there means you will get e power minus 2j omega. Like that. Next property, time reversal property. Time reversal property is nothing but Fourier transform of x of minus t is nothing but x of minus omega. So to prove this property, let t is equal to minus t is equal to any variable u. Dt will become minus dt. Dt will become minus du. So substitute here in place of t minus t, you substitute minus t and find out Fourier transform. Let minus t is equal to u. You will get, in place of x of omega, you will get x of minus omega. Use this equation, Fourier transform equation, to find out Fourier transform of x of minus t. So in place of x of t, substitute x of minus t and find out Fourier transform. You will get capital X of minus omega as Fourier transform. This is about Fourier time reversal property. Next property is time differentiation and frequency differentiation. So d by dt is nothing but differentiation of x of t. So if you apply Fourier transform for this, you will get j omega into x of j omega. Use the equation x of t is equal to 1 by 2 pi. What is this equation? This equation is nothing but inverse Fourier transform equation. So here this is nothing but inverse Fourier transform equation. Here you apply d by dt. So if you apply d by dt, you will get 1 by 2 pi as a constant, e power minus integral minus infinity to infinity. Next, x of j omega with respect to t, j omega is constant. So x of j omega will come outside. So only e power j omega t will be differentiated, will get differentiated. So e power j omega differentiation is nothing but j omega into e power j omega t. So that you will get j omega. Here you will get j omega, and that will be like inverse Fourier transform equation. So that j omega x of j omega, for that inverse Fourier transform is nothing but d by dt of x of t. So Fourier transform of d by dt of x of t is equal to j omega into x of omega j omega. Like that you can prove the property. And in this video I just explained the properties. Proof is not included, but it will be very simple. Use this expression and prove this one. You apply here differentiation, you will get this expression. Next, frequency differentiation property. It is also said to be time multiplication property. So here t is multiplied with the signal, no? So time multiplication. So if you multiply time with x of t and apply Fourier transform, you will get j into d by d omega of x of j omega. So how to prove this property means you can prove f of x of t, that is Fourier transform, is equal to minus infinity to infinity integral x of t e power minus j omega t dt. This is Fourier transform equation. In this Fourier transform equation, you apply differentiation. Here d by d omega is there, no? So apply differentiation for this to get RHS of the equation. So you will get x of t e power minus j omega t. If you differentiate this one with respect to d omega, so what you will get? What is the constant now? Minus jt as constant. So you will get minus jt outside. So t into x of t, you can write it as t into x of t. So Fourier transform of t into x of t is nothing but minus j. If it go this side, you will get j into d by d omega of x of j omega. So this is the initial equation, Fourier transform equation. Apply differentiation to the x of j omega with respect to d omega, and you can prove this property. So this is about time differentiation and frequency differentiation properties. Next property, convolution in the time domain. That is nothing but if you take Fourier transform of two signals, convolution implies multiplication in frequency domain. Convolution expression, take the convolution expression x1 of t convolution with x2 of t is nothing but tau is equal to minus infinity to infinity x1 of tau x2 of t minus tau d2 is the convolution integral. And in this convolution integral you substitute x1 of e power x1 of t. So like this you can write this convolution equation, apply Fourier transform. So e power minus j omega t dt, Fourier transform. So j omega t place minus j omega tau plus j omega tau. So minus and plus will get cancelled, no? That's why you can write and take common like this. So now this is Fourier transform of x2 and this is Fourier transform of x1. So x1 of j omega into x2 of j omega, like that you will get. So for this the initial equation is convolution equation. Take convolution integration. In that you modify it to get x1 of omega into x2 of omega, so that you can prove the property. So convolution property is nothing but Fourier transform of convolution of two signals is nothing but multiplication in the frequency domain. So next property, Parseval's relation, which is very frequently asked question, important question, important property. So that is nothing but the absolute sum of squares in time domain is equal to 1 by 2 pi integral minus infinity to infinity x of j omega modulus square d omega. So for this, first we will take integral minus infinity to infinity modulus of x of t whole square dt. How can we write a complex number? X into x complex is nothing but modulus of x of t whole square. So here x of t we can take it from inverse Fourier transform equation. So apply complex conjugate on both sides of the equation. After applying complex conjugate, e power minus j omega t will become e power minus j omega t. X will become x complex of j omega. So substitute equation 2 in equation 1. After substituting, 1 by 2 pi will come outside and x of j omega, x star of j omega, x of t e power minus j omega t dt, which is nothing but Fourier transform equation. So like this you will get x complex into x. So x into x complex is nothing but modulus of x square, Fourier transform of x of omega, x of t. So like this you can prove the Parseval's relation. It is very important topic. So these are the some of the properties: linearity property, time shifting, frequency shifting, time scaling, time reversal, and duality property. What is nothing but duality property means, if you apply Fourier transform for x of t, you will get x of j omega, and if you apply inverse Fourier transform for x of omega, that is in frequency domain, again if you apply Fourier transform, you will get capital X of t as its Fourier transform. That is nothing but duality property. Fourier transform of a Fourier transform of signal. Next property, differentiation in time domain, differentiation in frequency domain, convolution property, which is very important, multiplication in time domain. Next property, integration in time domain, and Parseval's relation also very important. I hope you have understand properties of Fourier transform. It is asked you to remember any 4 properties. Among all the properties, convolution property and Parseval's relation, both are very frequently asked topics. Thank you.